Speaker is Dea Mahalawi, who's going to talk about monotonic references and gradual typing.
Hi, everyone. So today I'll talk about how to make gradual typing efficient. So gradual typing is an approach to combine static typing and dynamic typing in the same language. And with gradual typing, you can put annotations anywhere. There's no restrictions. And also it's type sound. So we do type checking at runtime. And you can imagine this type checking can be expensive performance-wise. So the traditional way to support mutable state or references in a gradually typed language is to, each time we cast, one of the pointers in the program is to wrap it in a proxy. And every time we do a read or write from that address, we have to go through the proxy first and cast the value we read or write appropriately. So proxy differences, the values of that type can be either addresses or proxies. And this proxy contains cast information that we use when we cast at read and write sites. So this means at runtime, the program doesn't know if the thing we are reading from or the writing to right now is proxied or not. So the compiler typically has to compile some dispatch code at each read and write site. So this dispatch code basically distinguishes between if it's proxied or not. And if it's proxied, we do the casting logic. If it's not, we just do the read or write operation. So this can be problematic. So if you look at an example like quicksort here, so we quicksort a vector. So, but the dispatching logic is hidden, right? It's the compiler inserts it. But if we highlight it, it's in a lot of places, right? So in our recent paper at PLDI, we show that this overhead can be up to 20%, so this is in fully typed code. This is, we penalize the programmer. The programmer did the hard work and, have the program fully typed and still pays for extra overheads. So one approach to fix this is monotonic references, which makes sure that the only value in there. So one of the invariants of monotonic references is we make the heap more static each time we cast it. So using the type preciseness relation. So as you can see, this relation is transitive and it's also reflexive. So int arrow int is more precise than dyn arrow int than just dyn. So the star symbol here is the dynamic type. So yeah, the heap can evolve or progress along 2 dimensions. It can be extended by adding more elements to it, or can be more precise over time. So the good things about this is there's no proxies, no dispatch. Performance in static typed code regions matches. If your benchmark, for instance, fully statically typed, the performance in that benchmark will match the performance in a similar dynamic statically typed language. Also, operations on that reference in static typed code regions can be just compiled to load and store operations. So that's very efficient and fast. However, the story for partial typed code is not as good. There are complications regarding termination and correctness. And one of them is when we cast the heap, we basically can't just go and do that. We have to make the cast delayed in some sense and write to the heap first. So why we do that? Look, let's consider this example where we have a program that creates a pair on the heap that has a cycle in it. So it would look something like this. So the second projection is basically a pointer to the pair itself. And now at line 5 and 6, we have a function h that expects a reference with a certain type, right? So if we pass in the reference to the pair I just showed to that function, we will need to apply 2 casts to that same address. So the cast itself is cyclic in some sense. So if you go ahead and just do the casting logic without regard to without doing this delayed cast trick, we'll basically having the result of the first projection outside that address at the moment when we try to do the second cast on the second projection. So delayed cast can be defined by this grammar at the bottom here. So one problem with this from the point of space efficiency, I will talk about this in a bit. The problem with this is in the second element in that grammar, we allow nested casts on these delayed casts. So that's not space efficient. These casts can accumulate. So in general, space efficiency is important for Gradual type systems because if you allow them to accumulate, they can grow unbounded, and this causes very serious performance problems. So one of our recent results shows that in very simple benchmarks like Quicksort and Sev, some of the configurations of the partial typed code, we can see up to more than 1,000 X slowdowns. So to restore space efficiency or to integrate monotonic references in a space efficient calculi, we basically modify the grammar to take out that the bit for nesting, and instead we compose the old cast and the new cast. So to do that, we use a technology called coercions, and coercions is basically a combinators over types. You can think of them as a DSL for operations on casts. So here I define a coercion composition for reference casts or reference coercions. And for monotonic coercions, if we want to compose two casts on the heap, we take the greatest lower bound of the two types that we want to cast the heap eventually with. So the greatest lower bound basically takes the most precise information from the two types we want to cast the heap with into one type. And at the end, we prove space efficiency by having a bound on the composition height. So every time we compose two coercions, we are guaranteed that the coercion itself that we end up with is not bigger or taller than the two old ones. So in conclusion, we want to try to solve a problem with proxy differences that it has overheads in static typed code regions, and monotonic references does exactly that. And we also integrated it into a space efficient system. So, with this recipe, we can build an efficient Gradual type system. This semantics is fully mechanized in Agda, and it's on my GitHub. And that's it.
Okay. We have time for a question or two. So one thing I wondered actually was the relation with the previous talk. Jean-Baptiste showed a system for sort of automatically handling computation on cyclic data. If you had something like that, would it automatically handle the tricky cyclic casts in the heap, or do you need to do something more than just sort of a general memoization and not tying?
I'm not sure. That's a good question, actually. Yeah, I think I wouldn't say this is the only way to handle cyclic casts. So there must be other ways, of course. And yeah, this is a good point.
Any other questions? Okay. Will the next speaker come up? And let's thank Dave again. Okay, well, our next